This talk is about electrostatic potential, that is a scalar field that is associated to the presence of an electrostatic field in space. For the purpose of introducing the electrostatic potential, we consider the problem of a source charge, capital Q, here, that is placed at the origin of the coordinates, and that produces an electrostatic field E. Then we consider a probe charge, lowercase q, and we move this probe charge from a point P1 to a point P2 in the field of electric field produced by capital Q. And we compute for this reason the work done by the forces, and particularly the work done against the forces, so the negative of the line integral of the force along the path of, that we describe when we move the charge from P1 to P2. After carrying out the integration, we observe that this work results in the difference of two terms. These two terms are very important, and we use them to introduce the potential, the electrostatic potential. Now, if we use a probe charge of unit value, this same integral, this same work done against the forces of the field is now the line integral of the electric field. So the result of this integration is the difference between these two terms is the difference between the two values of the electrostatic potential at point P2 and at point P1, and is described by this line. As you see, the electrostatic potential, and in particular this work, doesn't depend actually on the path of integration, on the path along which we move the charge, the probe charge from P1 to P2, but rather on the starting point and on the ending point. So that in general, the potential at some point P in space is the potential at some point P naught that is taken as a reference, at which we have a value of the potential conventionally assumed to be V naught, minus the line integral from P naught to P of the electric field along the line of integration. We observe also that for what concerns the electrostatic field, if the loop along which we move the charge is closed, so if we move the charge along a closed boundary, a closed contour, the total line integral of the electric field is 0. Because we know that electric field comes from the gradient of a scalar function, and this scalar function corresponds exactly to the potential function. The line integral of the electric field is in fact the flux of the curl of E through the open surface whose boundary is the closed line along which we carry out the integration. This is 0, whatever is the line and whatever is the surface, and the only possibility is that the curl of the electrostatic field is 0. Since the curl is 0, there is a well-known property of the curl that a function whose curl is 0 can be described as a gradient of a scalar function, which is our electrostatic potential. So the definition of the electrostatic potential, V computed at point P2 minus V computed at point P1, is minus the line integral from P1 to P2 of the electrostatic along the line. So the increment of dV along a differential dl is simply minus E dot dl. And this can be also written as the gradient of V times dl, from which we derive the expression of the electric field that we already anticipated previously. The electric field can be written as minus the gradient of a scalar function that is called electrostatic potential. We see in this slide several formulas that defines quite arbitrarily the reference point and the value of the reference potential so as to define unique value for the potential at P, but it's very useful to define the reference point at infinity and the value of the potential as being null, so that the final expression for the potential in 3D due to a point charge is written here, is equal to the value of the charge, capital Q, divided by 4 pi epsilon naught times the distance from the charge itself. The result is written here. So the reference is now at infinity. This can be done for 3D problems. It cannot be done for 2D problems, as we see in a while. So we have this expression for the potential, and once we write the coordinates, the general coordinates of the capital Q, the source charge x prime, y prime, z prime, and the observation point P, x, y, z, we can express this potential as function of x, x prime, y, y prime, z, z prime. If we do not have a point charge distribution, but rather a volumetric charge distribution that is deployed in space, we can also write something very similar that is obtained by an integral over the full space of the charge density, rho omega, which is a function of x prime, y prime, z prime, divided by 4 pi epsilon naught r, in which r is the distance from the observation point, P can be set anywhere, to the infinitesimal point charge rho omega times the omega that is placed at r prime, x prime, y prime, z prime. So this is the expression of the potential in 3D when we use as a reference potential the potential at infinity that is set to be 0. In 2D problems, the situation is a little more difficult because the expression for the potential is, you see, the electric field produced by an infinite line charge whose linear density has a finite value, let's say rho L. This produces an electric field that is shown here, whose dependency on distance is 1 over the distance from the line charge itself. So once we integrate and obtain the value for the general expression for the potential that uses an arbitrary reference point and an arbitrary value for the potential, we can observe that we cannot set the reference point at infinity. We must set it to a finite value, so that we end with an expression for the potential that is unique only when we fix a reference point and a well-defined value for the potential at the reference point at finite distance from the charge itself. And the final expression is this one, in which we have the linear charge density, as you see, rho L here, divided by 2 pi epsilon naught, there's a minus sign, then there's the natural logarithm of the distance from the line charge divided by the distance of the reference point from the line charge plus the potential of the reference point. This gives a unique value for the potential also for 2D problems. So let's have a summary of all the equations of electrostatics. We have Gauss' law in differential form. It's written as the divergence of D, which equals the volumetric charge density rho omega. D, which is linked to E by epsilon naught, the constant epsilon naught. The divergence of E is therefore rho omega divided by epsilon naught, and E is obtained as minus the gradient of a scalar field, that is the electrostatic potential. So once we substitute, we obtain that the general expression and equation for the potential is the divergence of a gradient of V equals minus rho omega divided by epsilon naught. The divergence of the gradient is the Laplace operator, so we have that V is obtained as a solution to this equation that is called the Poisson equation, in which the source is the charge distribution, charge density in space, in which the operator is the Laplace operator.